Okay, so last time we dealt with a two-dimensional system, right? Particle on a ring. And this time, right, we're gonna, right, make system more complicated. We're gonna deal with the three-dimensional system, right? The particle on the sphere. And again, right, three-dimensional becomes more practical case, right? Because we live in a three-dimensional world. And you can see, right, once we raise the dimension, make the system more complicated, right? The solution, mathematical solution, gonna be more tedious and hard. Again, I don't expect you to actually solve that, right? Even in the homework or in the exam. But at least if I give you the system, you are able to tell me, right, how to solve them in each step, right? You don't need to give me the final answer, but at least you need to know, show me, right, what are the right steps, right? What are the strategies in solving this problem? Okay, so now since we have a particle in the sphere, we're gonna deal with the three-dimensional system. So again, right, remember, right, since it's a sphere, it's probably easier to use, right, spherical coordinates. Again, right, for the three-dimension Cartesian, we have x, y, z. And for the spherical coordinates, rather what we have is we have the r, we have the theta, and we have the phi, right? We have two angles, right, in the spherical system. So now we need to convert x, y, z into r, phi, and theta. That's what we need to do. Again, this is definitely a little bit more complicated. Again, right, start from the Cartesian system since we're in the three dimension, and if we ignore, right, if we don't look at the potential energy, the first thing is to write down the Hamiltonian, right? For Hamiltonian, we only have the kinetic energy term, remember, right? And since it's a three-dimensional system, we have the kx, ky, and the kz. And then, right, again, just expand it. We have minus h bar squared divided by 2m times both. Partial derivative, right, on each directions. So that's the expression. And again, right, we want to convert this into spherical coordinates. So what we're gonna do is to, right, this looks like this. We're gonna try to look at how to work on this, right? So this, again, I will just give you the final answer because it's really tedious to solve that. U actually equals to 1 over r times r plus 1 over r squared, and you have 1 divided by sine square theta alpha phi square plus 1 over sine theta alpha theta, the partial derivative sine theta alpha. Well, this looks very scary, right? Definitely it is scary, but here, since we know r is fixed, same as the particle in the ring system, right? This part should be equal to 0. And what we can replace here is use this angle square to name it, right? To give a new term is a Langevin, right? It's called Langevin. I don't know how to pronounce it, but it's Lagrangian operator, right? So in that case, we know that, right, this operator can be equals to 1 over r squared, and we have this Lagrangian operator. So with that, right, we can actually write down the Schrodinger equation, right? Minus h bar squared divided by 2m times 1 over r squared. And you have this, you have this operator applies on the both theta and omega and e, phi, theta, and omega. And again, right, two-word step, that's why expect you to know, right? And of course, the next step gonna actually solve it. Honestly, even for me, right, it takes me a lot of effort to try to work on that. And it's probably easier to just, right, use some mathematical software, right, to actually work on the solutions. So in that case, right, what I'm gonna give you is just directly give you the solution. All you need to know is, right, the step to solve that, right, and also the solution. The solution, what you find is for the energy part, right, we actually find there are two numbers, right, two numbers that is quantized, L and ML, that equals to L times L plus 1 h bar squared divided by 2i. And the L here is actually what we call the angular momentum quantum number. And you will find that, right, in this case, remember ML for the particle in the ring case is what we call the magnetic quantum number, right? In this case, you will find, right, the magnetic quantum number does not, right, in the normal condition without extra potential, ML does not really change the energy, right? So that means, right, no matter ML is at given angular momentum quantum number, right, there's a degeneracy, right? There's an energy degeneracy for ML. Again, that's on the case without external field. Once you have the field, right, it's gonna be a little bit more complicated than that. And again, right, that's all I expect you to know. And another thing that I expect you to know is that you have to look at the book, right, to look at, right, what does the wave function look like. Right, the expression of the wave function is actually very complicated, but you should check the book, right? At least look at the distribution, right, on the shape of those wave functions. And beside that, what I expect you to know is, right, once you have the 3-dimension, right, have a particle on the sphere, right, you're gonna use a spherical coordinates. And once you use the spherical coordinates, right, what we're gonna do is still, right, apply this expression, right, apply this energy operator on the wave function, right? Put in the Schrodinger equation. That's how you get the answer. And all you need to know, right, again, the energy solutions, right? Just know that, right, this angular momentum is quantized, and the magnetic quantum number, right, does not really impact, right, the energy if there's no external field. That's it.